Welcome to this joint Bark Meow seminar with Amir Yehudayoff from the Technion, who will tell us about how to slice the hypercube, or maybe how not to slice it, since it seems to be hard. Amir, without further ado, please.
Hello, everyone. I wish I could do this in person, but Zoom is now the way we do things. So I'm going to try to explain some ideas that are related to computational complexity, geometry, machine learning, somewhere in the intersection. And this is a joint work with Gal Yehuda, who is a PhD student at the Technion. Please ask me any question you wish. I also see the chat, so you can also write. So I'm going to start. So I'm starting with a very high level introduction. So the basic object I want to talk about is a geometric embedding of the Boolean hypercube. So the Boolean hypercube is a discrete object, but it can be naturally embedded inside Euclidean space, where points are just points in Euclidean space, and edges, for example, two different vertices that are different in a single coordinate are connected by an edge in the graph sense. So we can implement these edges as straight lines inside Euclidean space. So we have this geometric Euclidean geometry that lives around this hypercube, and this geometric representation is very important. For example, this allows to do optimization over the hypercube because we can do gradients and things like that in Euclidean space, and this optimization allows to do machine learning and things like more complicated operations. But in this talk, I'm going to focus on a very, very simple question. So we have the hypercube lives in Euclidean space, and there are the vertices and the edges. And now, because we live in Euclidean space, we have more structure. For example, we have hyperplanes. Hyperplanes in this talk will be denoted like this. So these are all the vectors z, so that their inner product with the normal vector v is some number mu. This is the notation I'm going to use. And this hyperplane, which is here, it's the green line, slices an edge, which is a straight line segment of length 2, if the two endpoints of the edge lie on two different sides of the hyperplane, like in the picture, or this is a way to algebraically define it. So now we have the hypercube lives in this Euclidean space, and now we can pass a hyperplane, and this hyperplane slice some edges of the hypercube, and now we see a geometry comes into the picture, and the question I want to understand, or where I'm going to focus on, is how many hyperplanes are needed to slice all these edges. So there are n times 2 to the n minus 1 edges. How many hyperplanes we need to slice all of them? Okay, so this is the specific question I'm going to focus on. And this question was studied for many years, starting in the 1970s. O'Neill studied it with motivation from machine learning that came from the perceptron's book, or the perceptron idea, that is one of the first ideas in machine learning. It was independently studied by Grunbaum in the context of geometry. And a bit later, 20 years later, it was studied in computational complexity. I will explain exactly why, by Hastad and Paturi and Sachs and many others. So there are many reasons to try to understand this problem. So this is a very quick background. Do you want to ask some question, or are we good? Okay. So first I want to explain two constructions of families of hyperplanes that slice all the edges. There are two very different constructions. One construction here on the left is n hyperplanes that are the normal vectors are the standard unit vectors. These are n orthogonal hyperplanes, and these n hyperplanes slice all edges. This is one construction. A second, very different construction is on the right-hand side. So this is a picture of the hypercube arranged in the direction 1, 1, 1, 1, 1. And the n hyperplanes are n parallel hyperplanes that separate some layer k and layer k plus 1. So these n hyperplanes slice all edges of the hypercube. And you see that there are two very, very different constructions, two also natural constructions. And the first question that comes to mind is, so here, this is n, this is also n, maybe n is the truth, maybe n is the correct answer to this question. And I would guess that from these two examples and from a little bit of thought, I would guess that the answer is yes, this is optimal. But Patterson showed that this is not correct. He showed that in 6-dimensional space, there are 5 hyperplanes that slice all edges of the 6-dimensional space. So this is by a very explicit construction that I did not show here. And now, after we have this construction, we can use it to get a gain in every dimension. So in dimension n, we can partition the n coordinates to roughly n over 6 buckets of size 6 each. And in each 6 coordinates separately, we use these 5 hyperplanes, and in the rest of the coordinates, we just write zeros. So we have 5n over 6 hyperplanes in this way. And it's fairly simple to verify that these 5n over 6 hyperplanes also slice all edges. So there is a subadditivity property in this problem. Okay, so and
is 5 hyperplane construction complicated, or is it like?
It's not complicated, but it sort of looks like some random numbers: 1, 4, 6, 8, and then -1, 5. Like, I don't see a structure, just some.
Okay.
And so, even though this is about 50 years ago, this is the best upper bound we know. So, so I guess nobody else also found a real structure in this construction that you can sort of exploit to get a better understanding.
Did people prove that it's optimal with a constant number of dimensions? I mean, you would kind of think that it wouldn't be hard for a computer to test all possibilities if the number of dimensions is not too high and see if something works along those lines.
I think that so up to dimension 4, I will mention it. This is the truth. So the first place so 6 is the first place we know how to get a gain. Mm-hmm. And for higher dimensions, the grid is not so small because potentially the numbers are between, say, -2 to the n to 2 to the n. And there are sort of maybe 30 such numbers in 6 dimensions. So I think, I don't know if somebody really tried to do this, but I don't think it will get us to 20 or something. But I don't know. Okay, so this is the best construction we know. And the topic I want to understand is how to prove a lower bound on these numbers. So the first person who proved the lower bound was O'Neill. This was in the 1970s. And he proved that we need at least square root of n hyperplanes in order to slice all edges. And I will explain his proof later on. And in some special cases that are written here, we know better lower bounds. So in dimension 4, there is nothing non-trivial. In general, if all entries in all vectors are positive or have the same sign pattern, then we must use n hyperplanes. This was proved by Alsvada and Zeng, and they proved something much more general. This is a corollary of what they proved. And this specific statement is, it's not hard to prove. I can explain it later if you wish. And a third type of lower bound was known if all the entries are in the normal vectors are either +1 or -1. In this case, also we need a linear number of normal vector or of hyperplanes. So this is the summary of what is known about this problem. And today I want to tell you how to improve this lower bound. So this is the first improvement in a long time. And I want to, this number is not so special. The current proof, this is roughly what it gives. I don't think it will give something much better, but I think the ideas can be maybe improved if combined in a more efficient way. So I want to explain to you how to prove this lower bound on this number. And also to show some interesting ideas that came while we try to prove some lower bound. Okay, so this is the goal. But before we do this, I want to explain 2 applications. One application is in computational complexity. So the application is for threshold circuits. So a threshold gate is a unit that takes a Boolean X and outputs its position according to some hyperplane, if it's on the positive side or the negative side of some hyperplane. And when we use these gates in a sequential way, we get a circuit that these are called threshold circuits. They are comprised of such gates. And this family of circuits is very interesting. For example, this is neural networks are of this form. Sometimes or typically the sign is replaced by some continuous gate, but this is the type of gates that appear in neural networks. And in computational complexity, these are also very important. And the very simple question that the slicing problem is related to is, what is the minimum size of such a circuit that computes parity, the parity function? So this question, so it's a very basic question, but it also relates, parity is about a finite fields, like it's an addition over a finite field. And this is such a circuit operates naturally in Euclidean space. So it's a simple question that relates Euclidean space and sort of finite fields. And we don't know the answer to this question. But the observation is that if we have a threshold circuit that computes parity, then the first layer of the circuit defines a slicing family. So this is the observation that relates this computational complexity question to the slicing problem. So here is a picture of the input layer of a threshold circuit. Then there are K gates that are connected directly to the inputs. And above them, there are some other gates that are connected to these gates. Now, every such gate is a threshold circuit, so it defines some hyperplane. And the observation is that if this circuit computes parity, then it must be the case that these K hyperplanes slice all edges. The reason is very simple. If there is an edge that is not sliced by these K gates, then all of them output the same value on the two opposite sides of the missing edge. So there is some edge that is not sliced. The two opposite sides, the circuit, all of these gates output the same value. But the parity of these two neighbors is different. So the circuit cannot compute parity if these gates do not slice all edges. So this is the first observation that connects the two problems. Was it clear? Yes? Okay.
Yes.
Okay. So now we can immediately deduce some lower bound in computational complexity. So O'Neill proved that the number of gates in the first layer is square root of n. And the corollary of what I said before is that a better lower bound is true. I want to mention that Paturi and Sachs, and in Pagliazzo, Paturi and Sachs studied, instead of the number of gates, the number of wires, and have some non-trivial statements in this on the number of wires, and this result also improves the lower bounds there, but I don't want to describe it quantitatively right now. I want to comment that about this question, there is a threshold circuit for parity of depth 2 with a linear number of edges. So there is a fairly simple depth 2 circuit for parity with a linear number of edges. And actually, maybe I will go back. This circuit is based on this slicing. So this slicing family allows to compute parity. So it's not complicated, but I don't want to do it right now. Okay, so this is the first application, a new lower bound in computational complexity. The second application I want to mention is a more combinatorial application. So here, the task we want to understand is slightly different. Up to now, we wanted to slice edges. Here, we want to cover vertices. So a hyperplane covers a vertex if the vertex belongs to the hyperplane. And a natural question to ask is how many hyperplanes are needed to cover all vertices of the hypercube? Now, the answer to this question is just 2. 2 hyperplanes suffice to cover all vertices. The hyperplane x1 equal to -1 and the hyperplane x1 equal to 1 cover all vertices. So this question is not so interesting. But a question that was asked before is, what if we insist that all entries in all vectors are non-zero? So they're not parallel to the x's, they're sort of generic. What then? Is there a better way to, is there a non-trivial way to cover all vertices? And so this is the question. And a theorem of Littlewood and Offord that was later improved by Erdős shows again that
so sorry, Amir. So cover a vertex is like hitting the vertex with the quality. So the hyperplane should really like cut through the vertex.
Yes, yes. Really, the vertex should be on the hyperplane.
Okay, I got it. Thanks.
Yeah. And so again, a lower bound of square root of n was known for this problem. And this is related to, so Littlewood and Offord studied this question in the context of number theory. And later Erdős improved their results. And a corollary of what of the theorem I just described is that also for this problem, the same lower bound holds. So it's an improvement over this lower bound. And the reason is that if we have a skew family of hyperplanes that cover all vertices, these are the red lines here, pictorially. If we take every such hyperplane and perturb its threshold a little bit up and a little bit down, just slightly, then we doubled the number of hyperplanes in this operation. But now this these gray hyperplanes slice all edges. Every single edge is sliced by such a hyperplane. Okay, so this is the second application. And now I want to explain some of the ideas in this proof. So the plan is very, very simple. The idea is, let's assume that there are very few hyperplanes, very few, let's say this few. Now we should locate an edge that they miss. This is the plan, to find some edge that they miss. Now the question is, how do we locate this edge? So what mechanism can we use to locate this edge? So we can try to use randomness, choose a random edge. This is not so effective because if we take slightly more than square root of n hyperplanes near the middle in the parallel family, we sliced a vast majority of edges. So the fraction of edges we slice is almost 1. It's 1 minus something exponentially small. So we basically have no chance to hit a missing edge if we choose it randomly. We can try to use algebra, sort of embed it in some linear algebra and try to use linear algebra or some other polynomial algebra. Somehow the hard thing is to capture the slicing property. It's sort of an open property. It's hard. I couldn't find a real algebraic way to even encode the problem. We can try to use topology. We couldn't find any way to use topology, although this may be an option. And eventually we came up with geometry, and now I want to tell you how does the geometry can help to do something non-trivial. Okay, so this is the starting point. We want to locate a missing edge, and now how do we do this? So this is part 1 of the argument. So the geometry that we are going to use is this first move in the proof is related to this problem in geometry. This is called Tarsky's Planck problem. And it's a problem in Euclidean space. I will explain it briefly. So we have a convex body. This is the green thing I drew here. And we want to cover the complex body by Plancks. A Planck is the region between 2 parallel hyperplanes. And the width of the Planck is the distance between the hyperplanes. So we have a convex body and we want to cover it by Plancks, by regions of this structure. And the question is, can we do something non-trivial? So the most efficient, obvious way to cover the convex body is to take such a Planck in the most narrow side of the convex body. This is called the width of the convex body. So this is the most efficient, obvious way. Now, Tarsky asked, can we do something non-trivial if we allow any type of configuration? Okay, so this is Tarsky's Planck problem. And it took, I think, 20-something years until Bang solved this problem. And he showed that if a sequence of Plancks cover a convex body, as in the picture before, then the sum of their width is more than the width of the convex body. There is no efficient way to cover the convex body.
So just putting the Plancks in parallel, that's like the most trivial and the best you can do.
Yes, exactly. Yeah. So this is called Bang's theorem, and Bang's proof, I will talk about it briefly, is quite amazing. It's very, very short, and Keith Ball isolated the following lemma from Bang's proof. So here is the lemma This is a special case of the lemma, but it suffices for us. So it's a lemma just about matrices, very elementary. It goes like this. We have a real valued matrix, M, and it is symmetric, this matrix. And it has ones on the diagonal. So all the diagonal of M is just 1, 1, 1, 1, 1. Then we choose a list of numbers, mu1, mu2, mu3 up to mu k, and some other parameter. So this is what we get as input. The output is the existence of a sign vector, +1 or -1, so that if we multiply M by this sign vector and look in the ith coordinate of this vector, we get a number that is far from mu I. How far? This parameter we chose. Okay, so it's a very elementary lemma. It's sort of, it's not obvious how this is related to this, but you can use this lemma to deduce this relatively easily. So, okay, so this is Beng's lemma. And the most important word in Beng's lemma is this exists. It tells us that there is some good object. Okay, this is the starting point of our search of this missing edge, this epsilon. I will explain later exactly how this is structured. And I want to say one more thing. The proof of Beng's lemma is 2 lines, 3 lines. It's like really, really short, and it's amazing. He defines using this M, mu, and theta some energy, a very simple energy, very natural energy. And this epsilon is the maximizer of this energy among all these points. So we just, and then you just verify that this is correct. So it's a very, very nice proof. And we are going to use this word. This is the most important word for us. Okay, so this is the first part in the proof, how we use geometry. Okay. Okay. A second ingredient in the proof is related to antichains. Okay, so I'm going to explain what antichains are in this context, and also describe some what I think is a nice statement. So here is the connection between the slicing problem and the idea of antichain. So this is the main observation here. This observation was made by O'Neill in his paper. So the statement is, if the normal vector V has only positive entries, and we look on the collection of edges that this hyperplane slices, then this collection of edges is an antichain. Okay, what does it mean to be an antichain? This is written here. It means this, the following thing. We look on a chain of edges. What is a chain of edges? A chain of edges is a sequence of n edges in the hypercube. It starts in the all -1 vector, and it ends in the all +1 vector. And we go from C1 to C2 by changing a single -1 to a +1. Okay, so this is a chain of edges. We just increase coordinates one by one. This is called a chain of edges. What does an anti-chain mean? An anti-chain means that in every chain, in every such chain, the number of edges that are sliced by this hyperplane is at most 1. Okay, this is what it means to be an anti-chain. Why is the number of edges that is sliced at most 1? Well, we start at a vertex, at the all -1 vertex. When we go to C1, the inner product with V just goes up. And when we go from C1 to C2, the inner product with V goes up. There is at most a single point, because it goes up, 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 where we cross the threshold mu. So at most once in all of these sequence of numbers, vectors, we cross the threshold. So we don't cross this twice. Okay, this is the observation of O'Neill. Is it okay? Was it? Yes, okay, thank you. And now this is how O'Neill proved his theorem. He proved that if we have a single hyperplane, any hyperplane, the fraction of edges from all the possible edges this hyperplane slices is small. It's at most 1 over square root of n. So to cover all, to slice all edges, we need at least square root of n, just in terms of counting. Now, how does his proof go? First, this is the observation we just described, that every hyperplane slices the collection of edges that a single hyperplane slices is an anti-chain. Now there is the sign pattern, which is not important. The sign does not change the validity or this much. So you can ignore the sign pattern. It's not important. And then he said Baker proved that the size of any anti-chain of edges is just small. It's at most this. This is a theorem of Baker. So this is how O'Neill's proof goes. First, he identifies that every hyperplane defines an anti-chain, and then he says anti-chains are small. This is it. This is O'Neill's proof. Okay. I want to move. So here we talked about anti-chains of edges because this is more related to the slicing problem. But the notion of anti-chains is more natural in a different context, is more well known in a different context. So I want to talk a little bit about this because it's related to part of the proof I'm going to explain. So here is the introductory slide to anti-chains of vertices. So we can identify this set with 0, 1 to the n, or all subsets of the numbers 1 to n. And now an anti-chain here is just a collection of sets that do not include each other. So there is no pairwise inclusion. They are incomparable in this order, in this partial order. And maybe the most basic theorem about anti-chains in this context is called Sperner's theorem. Sperner identified the maximum size of an anti-chain. It is the maximum binomial coefficient. This is Sperner's theorem. And I will explain a little bit how, so we will soon generalize it. So maybe I will not explain how to prove it right now. But now this is an equality. This is the maximum size of an anti-chain. And it is well known that this is an upper bound, or this is roughly this maximum. So we see this square root of n pops out. It's a fraction of 1 over square root of n of the vertices. And this is the reason for this Littlewood-Offord / R' theorem I mentioned before, this Sperner's theorem. So this is I guess this is taught in undergraduate classes, and at least I teach it. And I want to explain some new idea that is related to Sperner theorem. But before that, I want to explain or tell you about a generalization, a well-known generalization of this theorem. It's called the limb inequality. The limb inequality is a theorem on antichains, and as like Sperner's theorem, it says that the size of antichains is small, and it is written, this is the inequality. So we take the antichain, we partition it according to the size of the set. These are all the sets in the antichain that have size L. Then we sum over all L, and then we divide the size by the total number, and this number is at most 1. So this is called the limb inequality. And this inequality is stronger than Sperner's theorem because the maximum one, so this is at most 1 over the maximum times what happens when we delete this, which is the size of A. So this is stronger than Sperner's theorem. And this is very useful. This formalization is very useful. And I won't show a concrete example right now, but this is a very useful inequality when you study antichains. And I want to tell you about a generalization of this statement as well that we needed to prove in this, at least in our proof, in the proof we found. So the thing we needed is a version of these theorems for, instead of the uniform measure on the hypercube, for a general product measure on the hypercube. So now every bit has some bias, let's say. The first bit is 1 with probability 0.1. The second bit is 1 with some other probability, and so forth. This is what we needed. And this type of generalization was studied before by these 4 people who proved some non-trivial statements. They used a way to decompose a Bernoulli variable to Bernoulli variables, but their bound is analytical. They sort of computed things which make it non-sharp because they do estimations. So this theorem is not helpful for us, and we needed the correct answer. Otherwise, the bound, the lower bound we would have gotten was not interesting. So here's the theorem that we needed or that we proved. So it's a generalization of Sperner's theorem and of the limb inequality for general product measures. So there is a product measure on the hypercube, and there is an antichain A in the hypercube. Then the probability that a random element falls inside the antichain is small. It's at most the probability of getting hitting a single layer of the hypercube. This is a generalization of Sperner's theorem. And the limb inequality has a simpler form. So instead of dividing, the actual thing is conditioning. So this conditioning in terms of algebra is dividing, but here this is a different interpretation of the limb inequality. So this is a second theorem. And I want to explain how to prove these two things. Okay, so this is what I wanted to do for the rest. So I have one more thing for the first hour. So here is the main observation, the main idea. Okay, so now this lemma is the reason that both the Sperner's theorem and the limb inequality are true. So we have this product measure. Now we can define from this product measure a distribution on chains. What is a chain? A chain of edges. It's the empty set, then some singleton, then some two elements, one of them is here, and so forth, until we reach the whole set. So there is a distribution on chains, on such a sequence. What is the property of this distribution on chains? If we choose L, for example, L equal to 2, C2 contains two elements. This is the way it is chosen. It always has two elements. The property of C2 is that it is distributed like the distribution P, but conditioned on having size 2. This is the property of all of this chain. So the second element is chosen from P, conditioned on having size 2. The 10th element is distributed like P, conditioned on having 10, size 10, and so forth. Okay, so this lemma is just the existence of a way to choose such a chain. Does it make sense? I'm not sure.
So I'm not sure I'm parsing this, but so like, do you get a collection of chains in the end, or like what does it?
It's a distribution on chains. There is a way to choose a random chain.
Okay.
So we chose a random chain. Now we have n sets in our hand, n plus 1 sets.
Mm-hmm.
Now we have this object. The first set is empty. The second set in our hand has a single element. The third set has two elements. This is the type of thing we have in our hand, but it's random.
Mm-hmm.
Now, what happens if we just look on the third element in this chunk, and we look on the marginal distribution of this object, just the second one, it is distributed like a set chosen from the product measure, conditioned on having size 2. And this is true also for the first one and the third one. So there is a way to choose sets of all sizes in a way that they become an anti-chain, but they still have the correct distribution. Correct meaning like P tells us we need to choose them from. Okay, so I want to use the lemma, and I hope it will actually help to explain the lemma. So here is how, this is the proof, this picture. And I will try to explain how the lemma is useful, and maybe it will help to understand the lemma. So on this side, on the left-hand side, this is what we are interested in. We choose a random point from the distribution, and our goal is to prove that this random point lands on the anti-chain with small probability. This is the experiment we want to understand. So we want to prove that the chance of hitting this purple anti-chain is small. How do we do this? Well, instead of just choosing this point from this distribution, we do something different. First, we choose a full chain. This corresponds to like a full walk from the bottom to the top. Okay, now we chose this at random. After we did this, we choose, so now we have n+1 sets, all of this. Now, after we chose this chain, we choose a vertex on the chain according to the distribution of weights. So the distribution P gives some mass to vectors of weight to sets of size 0, some weight to sets of size 1, some weight to sets of size 2. And we choose a weight according to this distribution. So now we chose a vertex. So we chose a chain and a place on the chain. The observation is, or the lemma tells us, that this set is distributed according to the original P. Okay, this is the content of the lemma, or the conclusion from the lemma. Now, why is this useful? Because this set, this chain is a chain, meaning that A meets this chain at most in a single point. This is the definition of an antichain. Now, we need to choose among all the vertices on this chain. In order to hit the antichain, we must choose this single vertex. This is the only way we land on the antichain. Now, what is the probability to hit a single vertex? It is small. Okay, so this is just a sketch of the argument. Okay, so this is does it make sense? Maybe a little bit. Okay. Okay, so let me summarize the anti-chain part. We started with anti-chains are connected to slicing via O'Neill's observation. And we need some generalization of well-known theorems in order to use them in our lower bound. So this is the summary of this part. Now I want to, in the last part of the first hour, I want to just explain how does the proof look like. This is it, okay? And then I will give you more details in the second part. So, okay, so this blue thing represents the hypercube. Now we have few hyperplanes, and we need to locate an edge that is missing. This is the goal. So how do we find this edge? First, we use Bang's theorem, Bang's lemma, to locate some point inside the cube. Not a vertex, nothing, just some point inside the cube, inside this cube. Then we need to take this point and make it into a vertex or an edge. So we use linear algebra to push it almost all the way to being a vertex. I will explain this later. So we are almost a vertex. Now we take this vertex and randomly this, point, which is mostly on the, it's almost a vertex. We just need a little bit more. And here we use randomness again to make it into a vertex. So this is the process. We start with Bang and actually some randomness. We use linear algebra to drive it to the boundary. And then we use a little bit more randomness to make it into a vertex. And this thing will be missed, okay? So this is...
Sorry, what do you use Bang for? You just want to find some point that is far from all the hyperplanes? Or?
Exactly. Bang's lemma allows to find a point that is far from all the hyperplanes.
But it's just somewhere in the interior, so it's not a vertex at all. But you know it's like there's no hyperplanes in the general vicinity of this guy.
Yeah, so the hyperplanes will be far from it, but still this is not what we need. But it's a good way to start. This is the...
I see. Mm-hmm.
Okay, so maybe we will do a... How much time break do you want? Or
yeah, so I think then this concludes like the first regular seminar, the overview talk. So we suggest a 10-minute break. Thank you for the first half. And this is also a good time to ask questions. And then people can choose either so there's a 10-minute break, during which time you can just discreetly drop out. Or if you want to hear more about the hardcore details, then I guess that's maybe you can tell us a little bit what's going to happen after the break.
So yeah, the plan is to explain all of this picture. It's not going to be very, very technical because I think it's the high level ideas are enough, but I'm going to explain how do we use Bang, what does linear algebra mean, how does the randomness come here, and how the pieces come together. This is the plan for the next 50 minutes or so.
Okay, fair enough. So one question, is there any intuition as to what the right bound should be? Should it be linear or like n to the delta for some particular delta, or like?
So the best upper bound we know is 5n/6. I would not be shocked if there is a way to make it sublinear. This will not be shocking, like n to the 0.9. This will not be shocking to me. And if this is true, then now there is a game of some parameters, which I don't know where it should hit. The other option is that a linear number is the correct answer, but I also don't have a strong opinion on this. I just really don't know.
Okay. Any other questions? One observation is that connecting back to Mikkel's question at the beginning, it's a little bit intriguing. There has been some fairly recent progress on major open questions in extremal combinatorics using Boolean satisfiability solving and special purpose like special dedicated SAT solving algorithms that seem good for like hard problems. And the question is whether, for some small value like 6 or 7 or 8 dimensions or whatever, you could code something up and just brute force it and see if you can find some number. I have no idea at all, but like things like Ramsey type numbers have been like computed in this way.
Yeah, it is certainly reasonable to try to find in, I don't know, 8-dimensional space something better. But I'm not sure this requires like a real effort. Like a trivial way to code it, I think, will just take too long. We need to think.
So I think then why don't we just take a 10-minute break, and we'll be back at something like 12 minutes past 4 Central European time. Mm-hmm. So in 10 minutes from now. Thank you. So we're back from the break, And we will very soon let Amir speak. Just a philosophical question from my side, which you didn't address before the break, is like all these wonderful pieces of math that you're pulling together, like where do you find them? Like how do you know that it's Ball's lemma or Banks lemma that you need? I mean,
it's a very good question. It's like some what do you read in the morning?
it is just serendipitous discovery.
Yes, exactly. There is like so actually the story about the Tarsky Planck problem. I can tell you the story. It's quite a long story, but it's sort of by chance. There is no concrete, and it was unrelated to this in the beginning. It came from a completely different story. Maybe the most interesting thing is a mental image that I failed to portray. Is it's a connection, like sort of a geometric connection between the slicing problem and Tarsky's problem, which are in some superficial way similar. So formally both problems have hyperplanes, so this is good. So in the slicing we have hyperplanes, and in the Tarsky's problem we have hyperplanes. And now in Tarsky, the aim of the hyperplane is actually to cover the whole convex body. It's a very different objective. Here we have a much more sort of, I'm not sure that simple is the right word, but we just need to cut edges. It's a different type of objective. But you can imagine that if you have a slicing family and you somewhat inflate the hyperplanes, you get something that is close to covering in terms of Tarsky. Because if you slice an edge and slightly inflate it, you may include the vertex in the process, maybe, if you're lucky. If the hyperplane is in a direction that is has a lot of so this is true in some direction. This is almost true, actually. This very intuitive or just like a very vague statement. Mm-hmm. So this is a very vague connection between this problem and the slicing problem. And yeah, so I would say, yeah, now where did this problem came? So I thought it's about a year, maybe more than a year ago, I thought a lot about convex bodies. I wrote a paper with Emmanuel Millman about this. I can tell you about this, but this is a different story. And somehow it led me after some random walk to this Banks problem.
Okay, fair enough.
You mentioned that the number theorist Littlewood worked on this problem and solved this 0.5 lower bound. Yes. Did you get into depth of this number theoretic approach a little bit?
So Littlewood and Offord studied the problem. So the question they study is if there is a linear function with integer coefficients and all the numbers are non-zero, all the coefficients are non-zero, and we choose a random signing, what is the probability to hit 0 with this random signing?
I see.
They studied this problem because it is related. This is the main objective they try to understand. They studied the number of roots in random polynomials. This was their objective, which is somehow related to this type of, because the signing is the random coefficients of the polynomial, and you can imagine somehow it's related to the number of roots. It's not obvious at all, but
I see. But you didn't make use of any of those ideas?
No, eventually, actually, Erdős found a very simple proof using Sperner's theorem of what they needed. So,
okay, I see. Okay, thanks.
okay, so now that do you want to ask more? Maybe Mark, you didn't say anything, or Susanna, you also didn't say anything. You don't want to ask something? Okay, so I want to try to explain this this picture.
Please go ahead.
Okay, so we go this way. So this is what we want to prove, the lower bound. And there is a list of ideas, and I explained 2 of them. Now, for the rest of the talk, I want to explain these 4 ideas, and it will be very high level. So I ignored parameters and things like that. I don't think it will be helpful. So I want to explain these, actually, 3 ideas. This I will do in the end. So the plan is to explain another 3 ideas and then to just explain how the whole thing comes together. This is the plan. Okay, so no calculations of things like that, just a high level thing. Okay, so the next part is the understanding anti-concentration, but in a very strong sense. Okay, this I will tell you what I mean. So, okay, so this is the slide on this topic. So here we have a definition. The first part is a definition. So we have some vector in Rn, some list of numbers. We say that it has many scales if we can partition the vector, just like chunk the coordinates into S chunks. Some coordinates are here, some other coordinates are here, and some other coordinates are here. So just chunk it up. And there are many chunks, okay? Not very small chunks. And what is the property of this thing? V1 has the norm of V1 is much larger than the norm of V2. The norm of V2 is much larger than the norm of V3. And this is true for all of this sequence. So the name is sort of explanatory. It has many scales. There is a part of scale 1, then there is a part of scale 1 over 100, then there is a part of scale 1 over 10,000, and so forth.
So we should just think of, I mean, you're chunking up like coordinates of different sizes go into different V soup S's.
And so you will see how it is done, but this is a good intuition. Yeah.
Okay.
Okay, so this is what it means to have many scales. Now, the minimum scale is just the size of the smallest scale. Okay, this is the term I used. Okay. Now the lemma is whenever we have such a vector with many scales, we can choose x uniformly at random in the hypercube. So just a random signing to this vector. So this is a random number, some random variable. The probability to hit A, any A, is very small. Not only the probability to hit A is very small, also the probability to hit n times the smallest scale of this vector is small. So we have no way to hit A or anything close to it. This is the sort of the summary of this, okay? So if there are many scales, there is no way to hit a single value or even something in its vicinity. Now, this is relatively intuitive. For example, imagine that we have just the vector 1, then the second coordinate is 2, then the next coordinate is 4, then 8, so it sort of grows, and there are S scales. Now, if we choose a random signing, what is the probability to hit a single value? It's 2 to the minus S, because there are S, the binary representation is unique. So there is if we want to choose a number, there is a single signing that gives us this number. So this is the intuition, and this is some way to formalize it. Okay, so this is the first ingredient. If there are many, many scales, not a huge amount, but sort of this amount, then there is no way this V is useful somehow. It misses by a huge amount any hyperplane. If V is the hyperplane, then the probability that if V is the parameter of the normal of the hyperplane, and A is the threshold, the probability that X is near the hyperplane is tiny. It's not close by any sense to the hyperplane. Okay, so this is the third part, the first part in this head. Okay.
But for instance, I mean, both of the constructions you showed us in the beginning, they don't have many scales, right?
Yeah, there the number of scale is 0.
So you're somehow identifying stupid hyperplanes that we probably don't want to use. Is that the way to think about it?
Yes, exactly. Yeah, if somebody gives you this in the list, tell him go away. I don't believe you. Yes. Okay. So this is the third part. The next part is to identify some structure in this mess. And this is the slide about the structure. So this matrix has k rows, k is the number of normal vectors, and n columns. And the rows are the normal vectors. Now we can take any such matrix and partition it like this. What is written here? So we can find some number of rows with many scales. This part could be empty also, but some number. So this is the part with many scales. All of them are here on the right side after reordering the columns. And all the small scales of all of these vectors are on the left side. Okay, so we found some number of columns with many scales, some number of rows with many scales, and all of their smallest scale are in this part. This is one part of the structure. The second part is that in the remaining thing here, in this, the part that remains, every single column has very small norm. When we normalize the rows here up to here, to have norm 1. So, okay, let's see. If the vector here is 1, 1, 1, 1, 1, and we normalize it to have norm 1, then every entry is 1 over square root of n. Now, if k prime is less small, then 1 over square root of n plus 1 over square root of n plus 1 over square root of n, this is a small number. So the column will have small norm, actually L2 norm, but okay, this is the structure. So every column here has small L2 norm. All these rows are useless in the sense that they have many scales, and all the smallest scale is here. This is the structure.
And you're going to argue that you can always do this, or like, is it obvious that these seem to be fairly stringent structural requirements?
So you can always do this. Now there are parameters, which I basically ignored, but I can tell you how to prove it. So the idea is, if there is so let's start with a full matrix. Now, if all the columns have small norm, we are done. There is nothing. Because we are here. We have the structure. Now there is a column with small norm. Let's say we put it here. This column has a large norm, sorry. Okay. Now there is another column of large norm. So either we found okay, let's assume for a second that there is another column of large norm, and another column of large norm, and another column of large norm. Then what happens? We collect in this part, in the large norm, a lot of mass. We collected a lot of mass. What does this mean? That one of the rows must have a lot of mass, close to 1. So now we can sort of find one scale of this row. We found one scale of this row, because in these coordinates, which is a tiny fraction, we have almost all the mass, a mass more than 0.9, like a huge part of the mass. So all of this, the norm of all of these things is smaller than by a factor from this. And now you keep going until you stop. This is roughly the way this construction works. Does it make sense? Some sense?
I guess some sense.
So
I'm not sure where we're going, but yeah.
Okay, so yeah, right now I'm just trying to portray some statements, and then we'll see how it's going to merge.
Mm-hmm.
So the second part is a structure. Okay. The next part is this rounding, how we take, okay, so maybe I will do the picture here. So, okay, so I remind you the picture from before. We found some vector inside the cube. This vector came from Banks' lemma, and it is far from all the hyperplanes, as you said. This is, I didn't explain how, but this is something we found. Now we need to round it to a vertex. Now the first procedure in this rounding, I said, uses linear algebra. So this is the way it is done. For any such u, the coordinates in u are between -1 and 1. If all of them are either 1 or -1, we are very happy because it's a vertex. So let's assume that some of them are not 1 or -1. Now we can find some other vector, w. W has exactly the same inner product with all the normals as u has. So the w minus u lie in the orthogonal complement of all the v's. This is the same thing. So w is like u in the sense that all inner products are the same. W is still in the cube, but many coordinates in w are 1 or -1.
So it's like in a low dimensional cube somewhere.
Yeah, so most of the coordinates are 1 or -1, and maybe some of them are between 1 and -1, but a very few, like square root of n or some other number. Okay, so this is just linear algebra because these are k constraints. So we have n minus k's degrees of freedom. And you just need to think about it and see that this can be done. It's not a complicated statement. Maybe I will explain a little bit about the idea. So we start with u. Now we choose some vector that is orthogonal to all the vi's. And we add it to u with a coefficient that increases from 0 upwards. So sort of have u plus some t times this vector. When t is equal to 0, this is u. When t grows, one of the coordinates hits 1. Okay, so t grows, and then one of the coordinates hits 1, we stop. We gained one more coordinate that is either 1 or -1. And we keep going in this way. We add more and more 1s and -1s, and we can keep going as long as we have a vector in the orthogonal complement of everything we did so far. Does it make sense? Little bit. Okay, so this is the rounding part. And now I want to just explain how the whole thing comes together. Now, I think this is the maybe most interesting thing, but I will try to, please ask me a question about this. This is the part I actually most want to explain. Okay, so here is the type of argument. So we take the list of normal vectors and write it as a matrix. And we have this structure. Okay. Now we are going to do the 3 steps. So what are the 3 steps? So first we take every vector, this is just notation, vi. The part in this area is called prime, and the part in this area is called double prime, just notation. Now we want to find a vertex. So first we choose a completely random signing, completely random plus minus 1 vector in this part. Okay, this is x prime. What happens? X prime times this part has no way to be useful. This part has many scales. This is the smallest scale. No matter what we choose here, there is no way this thing will be sliced. Okay, so again, the high level idea, the part with many scales is completely useless. Okay, this is the first part. So what happened? All of these rows, we know they are useless for whatever is going to come next. This is the first part. Okay?
Amir, one question. I mean, we're looking for an edge in the end, right?
Yeah, this is true. I will come back.
But somehow, the way we're doing it, we're first rounding to a vertex.
Yeah, so I will explain exactly where so first mentally, I imagine a vertex, and then just a random neighbor of this vertex in some distribution.
And it somehow makes sense to first find the vertex, and then you're going to argue that then I guess many edges emanating from these vertex, or just that there's one?
Yeah, eventually you could argue that many, like some n to the epsilon.
Because, I mean, like just at a very high level, I would be happy if you just zoomed in on an edge instead, but somehow it's hard to do that. It's easier to zoom in on a vertex.
So from far away, there are so an edge is sort of a small thing.
Right. Okay. You're saying an edge. Okay. Once I found the edge, I just go to one of the endpoints, and they're like very close in some sense. Is that what you're saying?
Yes.
Okay. Yeah. That's right. Yeah. Okay. Yeah.
Okay. So this is the first part where we use the part of this structure. So all of these things are useless. So here I sort of deleted all of this part. We are done with all of this. So this is fixed. All the x's here are fixed. And all of these rows are useless. They can't do anything useful. Okay, so this is the step 1. Now we are going to use Banks' lemma. Okay? We are going to apply Banks' lemma to this part. So the matrix we are going to apply Banks' lemma with is this matrix, which I denoted here by V prime. This matrix times its transpose. So this is a symmetric matrix with one of the diagonals because we normalize the norm to be 1. Now, what does Banks' lemma tell us? It tells us that there is some sign vector that if we multiply m by this sign vector, we are far from all the mu i's, from all the sigma i's, sorry. So if we remember that m is of this sort, then we see that a vector u, which is this vector, so this is some parameter theta, we can ignore it for now. This is the list of vectors. Sorry, there is a transpose here, which this is a typo, times epsilon. So this is a vector in n-dimensional space. And what is the property of this vector in n-dimensional space? If we multiply v prime by this vector, we get a number that is far from sigma I. Okay, this is just Benck's lemma, just verbatim, with just moving things around. Okay, so we found a vector in the cube, so that it is a point in the cube that is far from all the hyperplanes. Okay. Now we need to make this point into an edge. So indeed, there are two things. First, this point is not a vertex. And second, we actually need an edge, not a vertex even. Okay, so we need two things. Okay. So first, we take this U and round it to an almost vertex W. This is using linear algebra. This part uses linear algebra. So U is far, also W is far. They have exactly the same structure, exactly the same. There is nothing changed. Okay. Now we have W. W is almost a vertex. Almost all of its coordinates are plus or minus 1. Now we need to make it into an actual vertex. How do we do this? We choose a vector x of plus minus 1s from a product distribution over the coordinates. These are the coordinates, n prime coordinates. And what is the property of this x prime? The expectation of x prime is W. Sort of, we want to round W to a vertex. How do we do this? We choose a vertex with a distribution whose expectation is W. Okay, so this is the way we take an almost vertex, W, and randomly round it to an actual vertex, x prime.
So you're saying W actually just exactly defines the distribution for us now?
Yes, so this is
basically the coordinates are just Bernoulli, like, I mean, we're sampling the x coordinates with Bernoulli W coordinate or something, kind of, sort of.
So the x prime coordinates are independent.
Yeah.
Now, what is the bias of a let's say the first coordinate? Let's say W1 is 0, let's say. Then it will be 1/2 to 1 and 1/2 to minus 1.
Mm-hmm.
If W1 is 0.8, then it will be, I don't know, 0.9 to 1 and...
Yeah, that's what I meant. Like modulo the affine shifts, it's kind of, yeah.
Yes, okay. Yeah. So there is a unique distribution of this sort.
Mm-hmm.
Okay. Now we chose a vertex and we choose Y to be a random neighbor of this vertex. And here we need some attention, but not so much. So I will not explain this randomness. It's not so important. But think about it just as a random neighbor of this vertex. Okay, so now we actually chose an edge. We chose X and a random neighbor of X. We have an edge in our hand. Does it make sense? Okay. Now we need to do the most of the work. We need to take care of all of these rows, which are actually, they don't have many scales. So they could potentially, this is the really interesting part. But we do know that the columns have small norm. This is what we actually know. What does it mean? It means that most rows have small norm. If all the columns have small norm, then relatively speaking, like up to some normalization, all rows have small norm. Okay. Maybe okay.
But like at a high level, I mean, before the rounding, we started off in a point that was already far from all of these guys.
Yeah, we started at a point that is far from all of them.
But now you're worrying that, well, we did a fair amount of rounding after all, and so maybe we somehow accidentally inched too close to some of these hyperplanes.
Yes, exactly. So when we did the rounding, there are too many of these to just abstractly say that we are far. So we need some additional structure. So the additional structure is that the norm here is small. Now, if the norm is small, then this random variable is very close to its expectation. So x prime times vi is very close to its expectation. And the expectation is large. It's very far from sigma I. This is something we know. This is how it shows the distribution of x prime.
So you're saying now that small norm will give us concentration?
Yes, if we have a small norm, then we get concentration. And so for most of these, the rest of the rows, for all of these parts, they have no way to, there are too few of them. Now there is very few final ones. This is the point. Now we are left with much less than square root of n. So the final one is that now xy is a random edge. And the random edge cannot, so we have a bound on the measure of antichains for random edges. This is the second part of the construction. So with the union bound, we can still handle this part. So we are left with very few rows. This is the final step. So overall, we choose randomly here. We start with bang here. We made most coordinates 1. Then we added some additional randomness. And then we were able to compile the whole thing. Okay, so this is just the high level structure. And now there are some parameters and more details, which I completely ignored because I think even this is, for me, needs attention, like needs concentration. So, okay, so this is it. I thank you for the attention and for the invitation.
So Thanks a lot also for the second half. So what in the end, what did you get? Like n to the point 57 was that, or 50?
57.
Yeah. Now if I want you know, n to the point 75 instead, so where am I? You know, where are we going to apply the hammer and screwdriver?
So in my opinion, the place where we should actually do something is Banks. So is Banks theorem. Yeah. So this theorem is meant, this lemma is meant to find a point that is far from all the hyperplanes. Even if we assume very strong structure on the hyperplanes, this lemma is not the right lemma to give the truth. So I think the thing to do is to find the version of this lemma that is actually suited for this problem, not for some other problem. I don't have a concrete suggestion, but this is where I would look at. And actually, the other side of this question is the upper bounds. Mm-hmm. In my mind, there is no reason that so this construction, the inductive construction, this subadditivity sort of combines two constructions, this construction and the construction with the unit vectors. Sort of this is the tensor product of the two constructions. Mm-hmm. There is no reason that some other more sophisticated tensor products cannot be used to, but I don't have a concrete, and if some tensoring will work, this immediately gives some power saving, like in Strassen's algorithm. The minute you get a saving for 2 by 2, you get a saving in the exponent. So, but it's no, I don't have a suggestion, just I would guess it wouldn't be shocking if there is a way to do some clever tensoring.
But and would you like when you, if you find good slicings, would you also expect them to go into, like, you get better threshold circuits somehow, or you know, better something else?
I would guess the answer is no. So the reason this thing gives you a threshold circuit for parity is sort of numeric. It's in my mind a coincidence. If you use, for example, this this slicing family does nothing. It sort of copies x1 to the next level. So here you actually did something. You summed all coordinates in this construction. Maybe I should mention in this context that one of the things Paturi and Sachs proved, where is it? Here, is they showed that if the coefficients are small, then a depth 2 circuit for parity cannot be much smaller than linear. So actually the number of wires in the circuit is at least n squared over log squared the magnitude of the coefficients. This is what they proved. It's a very, very nice proof. Really, really nice. They use a approximation using rational functions in a very, very nice way, really nice.
Any other questions before we officially declare today's seminar over? So it seems that maybe we call it a day. So
thank you very much, Jacob.
Yeah, unless someone like intervenes in the next 15 seconds. So thank you again for a wonderful seminar. This is great. And yeah, as soon as circumstances allow it, I guess we'll do this in person instead. But for now, we're happy to have Zoom.
Yes.
All right. So thank you so much. Thank you.